The moon near the horizon is not bigger. And if you've ever seen it looking enormous, orange, heavy, almost close enough to touch your eyes weren't failing, what changed was your brain's model of space. And in a few minutes, we'll do a simple reality check that makes the giant moon shrink without the moon moving at all. When I say the moon is an optical illusion, I don't mean the moon is fake. I don't mean it's a hologram in the science fiction sense. And I definitely don't mean the moon is physically changing size. The moon's diameter is about 259 miles. That doesn't fluctuate because it's near the horizon. What you're seeing is a mismatch between two things. One, the image the moon forms in your eye. Two, the interpretation your brain builds from that image. Here's the key point. The moon's angular size, the fraction of your visual field it occupies, stays almost the same whether it's overhead or near the horizon. If you take a photo with the same lens and the same zoom, and you don't change the framing, the moon comes out nearly identical in size in both cases. Yet to you, subjectively, the horizon moon often feels dramatically larger. So where does the extra bigness come from? Not from the atmosphere magnifying it like a lens. In fact, the atmosphere tends to do the opposite of what people assume. When the moon is low, refraction can slightly distort it, often flattening it a bit vertically. That's why you sometimes see a subtly squashed moon at the horizon. It's real, but it's not what makes it look gigantic. The giant moon is mostly a perception effect, which raises a strange question that sounds philosophical but turns out to be practical. If the picture in your eye stays almost the same, how can the experience in your mind change so much? Hold that question, because answering it will also explain something else that's easy to miss, why your camera and your brain disagree about the same sky. We tend to think vision works like this. Light enters the eye, the brain receives an image, and consciousness sees the image. But that's not how it feels to be a person. You don't experience pixels. You experience a world. A stable world with objects that have sizes, distances, and meanings. Your brain is less like a security camera and more like a prediction engine. It takes limited data and produces a usable model, what is out there, where it is, and what you can do with it. A helpful analogy is temperature. Temperature feels like a simple property, hot or cold. But at a deep level, temperature is a summary. It compresses the chaotic motion of countless molecules into one number that's useful for everyday life and for engineering. Temperature is real. It matters. But it's not fundamental in the way molecules are. Your perception of size is similar. Size, in your experience, is not just geometry. It's geometry plus interpretation. Your eye receives angles. Your brain infers distances. Then it constructs the size of objects in the world. And that inference step is the quiet source of the moon illusion. If you ever want to feel how direct the illusion is, do this. When the moon looks huge near the horizon, compare it to something you know the size of in your visual field, like your thumbnail held at arm's length. Most people are surprised by how small the moon's angle really is. Roughly the width of your pinky nail at arm's length. And if you repeat that comparison when the moon is high overhead, it's basically the same. So why does the horizon moon feel bigger? Because near the horizon, your brain has what it loves most: context. Depth cues, perspective, layers of haze, trees, buildings, mountains, a ground plane stretching away. Overhead, the sky is sparse. It's harder to anchor. The moon illusion is what happens when your brain tries to do something very reasonable judge size using distance, while the sky gives it unreliable information about distance. There's also a little trick that makes many people notice how interpretive this is if you view the horizon moon in a way that disrupts your normal sense of up and down, like briefly looking at it upside down. The illusion often weakens. That doesn't prove a single theory by itself, but it hints at the real theme. The illusion lives in your brain's seen understanding, not in the optics of the moon. Now let's make the claim precise. There's a specific relationship, well known in perception science, that sits right under this phenomenon. Your retina doesn't measure size, it measures angles. A small object nearby can cast the same angular image as a huge object far away. So, to build a stable world, your brain mixes two estimates: the angular size of the image, the perceived distance to the object. From those, it constructs perceived physical size. This relationship is so central that it shows up in classic illusions like the Ponzo illusion. Two identical lines look different in size when they're placed on a background that suggests depth, like railroad tracks converging in the distance. Your brain interprets one as farther, so it scales it up. The moon illusion looks different, but the logic rhymes. When the moon is near the horizon, your brain tends to interpret that region of the sky as farther away than the sky overhead. Why would it do that? Because the horizon is where the world is. It's where distance lives in everyday experience. The horizon is crowded with cues that normally correlate with distance. Objects partially obscure each other. Atmospheric haze reduces contrast with distance. Parallel lines in roads and buildings converge. Texture gradients on the ground change smoothly. And you spent your entire life watching things recede toward the horizon. Overhead, those cues mostly vanish. The sky becomes a kind of blank canvas, so the brain's internal model of the sky often becomes a dome, and not always a perfect dome. Many people perceive it as slightly flattened, like a bowl. In that model, the horizon can feel farther away than the zenith. Now here's the crucial step. If your brain concludes the moon near the horizon is farther, but the moon's angular size on your retina is basically unchanged, then the brain's size distance scaling can make the moon appear larger. Same angle, larger inferred distance, larger perceived size. That's the simple version. Is that the final answer agreed upon by everyone? Not exactly. The moon illusion is famous partly because it's stubborn. Researchers debate which cues dominate, and different people report different strengths depending on environment, expectations, and how much foreground context is present. There are several families of explanations. One emphasizes perceived distance and the sky dome model. Another emphasizes relative size contrast. The horizon moon is seen next to trees and buildings, giving your brain a local frame of reference, while the overhead moon floats alone. Some emphasize how your eyes focus and converge, and how those oculomotor signals may conflict with the far sky interpretation. And some hybrid models combine these into one weighted estimate. But across these debates, one thing is very stable. The illusion is mostly perceptual. It's not the moon changing. It's not a lens in the air. It's your brain doing what it always does, turning limited data into a world. Now, here's the part that makes this more than a fun party trick. This illusion is also a gentle introduction to a deeper idea. Sometimes, what feels like a three-dimensional reality can be described by something that looks two-dimensional. That's a perception statement. But strangely, it also echoes one of the biggest surprises in theoretical physics. So, we're going to take a careful detour into black holes, not because black holes cause the moon illusion, but because they force physicists to rethink what it means for information to live in space. And then we'll come back and see the moon again, with new eyes. In everyday life, you expect that if you have a region of space, say a box the amount of information you can store inside scales with volume, bigger box, more room, that intuition comes from experience and from classical physics. If you pack more stuff into a space, you can encode more information, more arrangements, more possibilities. Black holes complicate this. In the 1970s, work by Jacob Bekenstein and Stephen Hawking revealed something startling. Black holes behave like thermodynamic objects. They have entropy. They have temperature, they radiate, and the entropy of a black hole scales with the area of its event horizon, not the volume inside. Area, not volume. That is not a small detail. It's a clue that our naive picture of inside and information might be wrong at a fundamental level. Then comes the black hole information problem. Hawking's early calculations suggested black holes radiate in a way that looks thermal, and if a black hole evaporates completely, it seems like the detailed information about what fell in might be lost. But quantum physics, as we understand it, strongly resists true information loss. In quantum theory, evolution is supposed to be reversible in a precise sense. If you know the exact state now, the laws preserve enough structure that, in principle, the past isn't erased. And so black holes became a battlefield between gravity and quantum theory. Over decades, many physicists argued that information is not destroyed. And modern developments, especially ideas involving quantum entanglement and space-time geometry, support that mainstream direction. Though the full story is technical and still an active research frontier. What matters for our intuition is the shift this debate encouraged. Maybe the bookkeeping of what can happen in a region of space isn't stored the way we thought. Maybe a region is, in some deep way, defined by what happens on its boundary. This line of thought is closely associated with the holographic principle, developed by physicists including Gerard 't Hooft and Leonard Susskind. The idea that the physics inside a volume may be fully encoded on a lower dimensional boundary, like a hologram that stores a 3D image on a 2D surface. To be clear, this doesn't mean the world is literally a projected movie. It means the most fundamental description of a region might use fewer dimensions than the world appears to have. Yet your mind produces a three-dimensional world. That doesn't prove holography in physics, but it gives you a human-scale intuition for how a boundary can contain enough information to generate a volumetric experience. And that's exactly why this detour is worth taking. Because the moon illusion is a case where your volumetric experience of space distance, depth, size shifts, even while the boundary data stays almost the same. Your eyes capture an angle. Your brain builds a world. In physics, something similarly counterintuitive may be true. What we call space might be a derived description, emergent from more fundamental information. And there is one celebrated place where this boundary bulk idea becomes extremely concrete. In 1997, Juan Maldacena proposed a remarkable duality known as AdCF-TET. Here's the intuition without equations. It suggests that a theory of gravity in a volume of space, the bulk can be equivalent to a theory without gravity defined on the boundary of that space. Two different descriptions, same underlying physics. It's not just a metaphor. In the settings where it applies, it's an exact mathematical relationship, and it has become one of the most powerful tools in modern theoretical physics. But it comes with an important caution. AdCFD is best understood in a universe with a particular kind of geometry called anti-de Sitter space. Our universe, on large scales, looks closer to a different geometry, associated with accelerating expansion. So our cosmos is not literally the same setting. So the honest framing is, established AdCFD is a major result and a proof of concept that holographic descriptions can be exact in certain model universes. Speculative. How directly these ideas map onto our universe in full detail remains an open research question. Now, bring this back to the moon. The camera gives you something like a boundary record, a fixed mapping from incoming light to a 2D image. Your brain does something like bulk reconstruction. It infers a 3D world of objects and distances. But unlike the mathematical cleanliness of AdCFD, your brain's reconstruction is not trying to be fundamental physics. It's trying to be useful. It uses shortcuts. It leans on context. It makes assumptions that work almost all the time. And the moon illusion is what happens when those assumptions get pulled in two directions. The moon's angle says, nothing changed. The horizon context says, this part of the world is far. Your brain merges those signals into one experience, and that experience feels like the moon swelled. Now we can say something subtle and important when your perception is wrong. It isn't random. It is systematically wrong in ways that reveal the rules your brain is using. So what are those rules exactly when you look at the sky? Let's talk about emergence and why it doesn't mean anything is unreal. There's a word that shows up both in neuroscience and in physics, and it's easy to misunderstand: emergence. Emergent does not mean imaginary. Emergent does not mean useless. Emergent means real at its level, even if it's built from deeper ingredients. A whirlpool is emergent. It's not a fundamental particle, but you can point to it, predict its behavior, and get pulled into it. Money is emergent. It's a human construct layered on paper and digits, but it can buy food, move armies, and shape history. Now consider the space you experience. You don't consciously see angles on a retina. You see a room, a street, a horizon, a sky. That space is an internal model, continuously updated. And most of the time, it's astonishingly accurate. But the sky is a special environment because many of the cues your brain normally uses to calibrate distance don't work well at astronomical scales. Binocular disparity, the difference between left and right eye views, works wonderfully for nearby objects, but for the moon, it's essentially negligible. Accommodation and convergence, the focusing and inward turning of the eyes also become poor distance signals at such extreme distances. Motion parallax, how nearby objects shift quickly as you move, doesn't help much with something that distant, unless you have a strong foreground reference. So for the moon, your brain relies heavily on scene context. When the moon is near the horizon, the scene is rich: trees, buildings, landscape, haze, perspective. The brain can place the moon into a structured world. When the moon is overhead, there's less context, and many people report it looks smaller or simply less dramatic despite being the same physical object, with nearly the same angular size. This is also why the illusion can change depending on where you are. If you're in a city with a skyline, the horizon moon can look monumental. If you're at sea with a clean horizon and fewer depth cues, the illusion can weaken. If you're in a place with strong atmospheric haze and layered distances, it can intensify. And this brings us back to a deceptively simple sentence. Your camera sees one moon, you see another, not because the camera is more truthful, but because it's doing less interpretation. A camera records light patterns, a brain reconstructs a world. Now, what about that upside-down effect? Why does disrupting orientation sometimes reduce the illusion? Because your sense of horizon, ground, and sky is part of the world model. When you invert your view, the brain's usual assumptions about scene geometry and depth cues become less stable. The horizon stops behaving like the horizon in your internal map, and the scaling can relax. Again, that doesn't pick one final theory, but it aligns with the central idea. The illusion is tied to your brain's interpretation of space, not to an optical magnification in the air. At this point, we can say something that sounds dramatic, but is actually modest. The moon illusion is a reminder that perception is an interface. An interface is not a lie, it's a translation. It hides complexity so you can act. And now that we've built the machinery, we can return to the moon and state the explanation cleanly without mystery. The moon does not get physically larger at the horizon. Its angular size in your eye is nearly constant. The giant moon is mostly a perceptual effect caused by how your brain interprets the sky near the horizon versus overhead. Near the horizon, depth cues and the ground plane can make the sky feel farther away. When your brain combines that farther inference with the moon's unchanged angular size, it can scale the moon up in your experience. Other factors can contribute too: foreground comparison objects, scene composition, and the way your visual system resolves ambiguous distance cues in the sky. That's why it can vary. Sometimes it's overwhelming, sometimes it's subtle, sometimes you can almost switch it on and off by changing your viewing context. And importantly, this is not a failure of your brain. It's the cost of having a visual system that builds a stable world from incomplete data. Now we can talk about what this implies about the moon, about cameras, and about the way we think about reality. First implication, photos don't settle the argument because photos answer a different question. A photo captures angular size. Your experience includes inferred distance and world context. So when someone says, "Look, the photo proves," it's not bigger. That's true in one sense and irrelevant in another. The photo proves the moon's angle didn't expand. It doesn't address why your brain scaled it in experience. Second implication, the horizon doesn't just frame the moon, it can actively change your perception of it. When the moon floats in a blank sky, your brain has fewer distance cues, and the moon may feel smaller. When the moon sits on a horizon packed with depth cues, your brain has a richer model of distance and scale, and the moon can feel bigger. Third implication, this is a safe, everyday example of a deeper scientific idea. In physics, black holes forced us to confront a strange possibility. Information in a region may be constrained by surface area, not volume. The holographic principle suggests the boundary can, in some sense, encode the bulk. AdCFT shows that, at least in certain model universes, boundary and bulk descriptions can be exactly equivalent. Your brain doesn't prove those ideas, but it gives you intuition for them. A two-dimensional boundary can support a three-dimensional world if there is a rule for reconstruction. Your retina is a boundary. Your experience is the bulk. And the moon illusion is a moment where the reconstruction rules become visible. Now, one final clarification, because this is where people get misled. Calling something emergent is not calling it unreal. The moon you see at the horizon matters. It moves people, it anchors rituals, it changes photography, architecture, poetry, calendars. It is psychologically real, and that reality has consequences. But it isn't a direct measurement instrument, it's an interface. And once you see that, the illusion becomes less like a trick and more like a revelation, a glimpse of the mind's hidden geometry. So here's the full story. In one breath, the moon near the horizon looks bigger mostly because your brain uses context to infer distance and then scales perceived size accordingly. The moon's angular size barely changes, the atmosphere doesn't magnify it into a giant, and your camera records a stable angle while your mind constructs a changing world model. And that's why this illusion is so enduring. It isn't really about the moon, it's about what it means to see. Physicists like Leonard Susskind have argued that at the deepest levels, space itself may be an emergent description tied to information and boundaries. That's a separate, highly technical domain, but the moon illusion offers a gentle everyday echo. A boundary image can generate a volumetric experience, and the bulk you live in depends on reconstruction rules you don't normally notice. The moon didn't change, the model did. If you want more long-form science documentaries like this, where everyday experiences connect to deep ideas in physics and cognition, subscribe. And here's the question to leave in the comments when you see the moon near the horizon. Does it look dramatically larger to you? And does changing your viewing context, like isolating it in an empty sky, make the effect weaken?